I did scalar multiplication a different way on your homework. And then I asked you, is it still a vector space? So the first thing I was thinking of when I was sitting at my desk is, maybe I'll give you a different definition of scalar multiplication, and it ended up being a vector space still. For example, I could do this. I could define scalar multiplication like this. I think it still works. At least when I was sitting back and thinking in my chair the other day, I was like, I think that actually works. You actually can go through all those 7 properties and everything checks off just fine. So I can choose to define it this way. My scalar multiplication, it's weird, but it works. It does everything it's supposed to do in those 7 properties. So under that definition of scalar multiplication with the usual component by division, it comes out to be a vector space. So I was trying to think of something that won't work, so I made up something that won't work for your homework. So it's going to screw up some of those rules. By the way, this definition back here, it's a checklist. I put little boxes next to it because what you'll do is check through and say, is this true, is this true, is this true? One of my physics friends I went to a place that was when they said liberal arts school, it was an emphasis on the liberal. So we had a lot of pure math classes, and we had physics majors taking some of those classes. And one of the physics majors said, that's not a real proof, that's a check proof. So it's not like you have to go through the wiki or anything. You just go through and check 1, 2, 3, 4. Yep, satisfied them all. It's a vector space. Okay, so if I define it this way, and then I have to define what I mean by addition. So this is what I mean by addition, to combine those two. Then under those two conditions, this is what we call a real vector space, meaning that it's a vector space over the real numbers. The field is the real numbers. Now, so I didn't define this. This means the field is the real numbers. I gave you one in your homework where the field is not the real numbers. So you could have scalars coming from a different field. For electrical engineering, you need complex numbers to be a field. Did you have to take double E classes?
Only like one.
I think I'm sure that in the upper level electrical engineering classes, they don't use real numbers anymore. You have to use a complex. There's no way you can get around it. Okay, so you're all looking at it going, okay, so what? I'm not going to go through that checklist. That is the most, it makes set theory look exciting. It's the most boring proof ever. You had mentioned something in your thing. I'm sorry, it's boring, but I have to go through all these cases. It's kind of like that. It's like 7 things that you have to check, and it's like, ugh. But I was debating whether to make you guys do it, and I thought, oh, yeah, this is one of the proofs that you have to do. So whether I like it or not, it's not the point. I still have to ask you to do it. So that's why I'm asking you to do it. So here's one you should have got in your linear algebra class. If you haven't taken linear algebra, Colonel Clark says that all data science majors should take linear algebra. It's one of these classes, if Colonel Clark and I had our own way, we would teach stats using linear algebra, because all of stats turns out to be about matrices. And so it's a lot easier. Everything comes out a lot easier if you have that structure underneath it. But if you didn't have it, cubic polynomials. That means polynomials that are of this form, where the coefficients are real numbers, turns out to be a vector space. I have to define what I mean by adding the vectors, and adding the vectors just means adding term by term and pulling out the coefficients. And I can define scalar multiplication the way you'd think you'd have to do scalar multiplication. And under these conditions, this is going to be a vector space. You even have an I, J, K, you have a basis. Remember I, J, and K from 205? In 3 dimensions, you had these vectors that you always wrote. Is that how you guys write out vectors in 205 and 255? So the I, J, and K are what we call basis vectors. There's a basis here too. So you have all that same stuff that you have for R3. This will be R4. This will be like R4. Okay, any questions on this? If you're zoning out, please on your end try to like pay attention and take notes. It's not a Netflix show. Like you really have to kind of absorb some of it, or otherwise you'll be in pain when you start going through your homework. I see a lot of glazed eyes and no pen movement. That's why I'm like looking at it and going, oh. Okay, no more questions?
I think I'm having a hard time figuring out like what a vector space is still. Like if it's a set, I think it would
It's a set that satisfies those 7 conditions. Once addition and scalar multiplication is defined.
What would the elements of that set like? What is an example of something that's in that set?
So in this one, it's easy. Like I can write something down like this is an example of something in the set. Right? In the next one that I showed you, that's an example of a vector. That whole polynomial is an example of a vector. Are quadratic polynomials in here?
Yeah. Just make it.
Some of you say no, some of you say no. Yes. Look at the definition of the set. I have to go back up to the definition of the set. Always the definitions. Preciseness. Can a quadratic be in here? Okay. Those of you saying yes, why do you think yes? Kate?
Because A3 has to be an element of the reals, and zero is an element.
That's right. So I've uncovered quadratics are in here too. Are constants in here? Is 1 in here? Dash, why do you think 1's in here?
Same idea, you just said A1, A2, and A3 is 0, and you said A0 is constant.
Yeah, that's right. So constants are in here. So all of those things, smaller polynomials are in here by definition. So you always go back to the definition. So there are some things that are in there.
So, and you said the space is in R4.
It is R4. So there's this one theorem. There should be like bright lights and music when they play it. They don't play it, but when Dr. Clark walks in, there should be walk-on music when he does this theorem. And that's that all linear, all of these spaces, these vector spaces that are finite dimensional, which it is, are really just R1 through Rn. They turn out to be the same thing.
So like how what component of this makes it R4? Because I was like, it's only got an X and there's no other.
Because the
variables.
basis vectors are 1, x, x squared, and x cubed. There's 4 basis vectors. So every single element, every single polynomial can be expressed as a linear combination of those 4 vectors. And because of that, it's really just R4.
So the number of bases.
The number of bases tell you that.
Okay.
And all linear functions are just matrices, no matter what. That's like the coolest theorem. And I remember sitting there as an undergrad going, so the teacher was all excited and she's a lunatic. I'm not going to have anything to do with this major after I'm done. That's what I was thinking. I was only a sophomore. Okay. Maybe I should